All right, guys, last unit, Science 10, your cheer here. Okay, now we got to go over some kind of basic stuff. Some of it's going to be a review because you've probably taken this in like grade 7, grade 8, or grade 9. We're just going to kind of add to it a little bit. But for today, we're going to talk about climate. Okay, we're going to talk about the components of climate. Okay, the components of climate are the things you would typically associate with like a weather report. All right, when you look at the weather network on your phone in the morning, you know, on the app or whatever app you use for that, okay, you're going to look for, is it going to rain? Is it going to be windy? Am I going to see the sun? Okay, and how warm is it going to be? Right? That's what we're looking at. That's the kind of things we want to know, okay, when it comes to the weather. Well, the climate is the prevailing weather at a location. So it's what we could expect the weather to be like. Right? Now, if I describe the climate of an area to somebody, it seems weird. Right? So here's, for example, I'll give you this. The average temperature in this particular place is about 5 degrees Celsius. Winds are typically out of the southwest. Precipitation is, let's say, in the neighborhood of about 50 millimeters per month. And the average day length is 12 hours. Where is that place? It's here. Right? But I gave you the averages. I could say the average daylight anywhere is 12 hours. I mean, if I go to the equator, it's 12 and 12 every single day. But here, it's, you know, it's shorter in the wintertime, longer in the summertime, but it works out to an average of 12 hours of daylight every day. Okay? It's an average. Obviously, not every day is it that way. Right? That's why describing the averages for a place doesn't make a lot of sense. Right? It would be more accurate to say, you know, the amount of light in this place varies. So sometimes during the year there's very little sunlight, and sometimes during the year it hardly ever gets dark. You know, the temperature ranges from, you know, well into, you know, the minus 20s for part of the year to, you know, up to 30 degrees Celsius sometimes of the year. And, you know, some months are rainier than others, but that precipitation can come as snow, it can come as, you know, as rain, as hail, as whatever, right? It wasn't as descriptive as what I just said to you, okay? Which is obviously would have given you a better idea of where I was talking about. Okay. Then we want to talk about the factors that affect climate. And the big challenge here is to keep those things in your mind separate because they are different. Okay. The components of climate are the things you would associate with weather. The factors are the things that affect how much rain you get, how much sun you get. Okay. All of that kind of stuff. You guys follow me there? So the factors that affect climate are things that are not part of the weather. Okay. They're the things that affect the weather. All right. So we got to keep them straight. We also want to look at the effect of climate on plants, animals, and humans. Look at energy inputs and outputs. Okay, what's the main energy input for basically every ecosystem on Earth? The sun. Okay, everything on Earth, if it's natural, runs on solar power, runs on photosynthesis, in fact. Okay, if you're an animal, well, you either eat plants or you eat the animals that ate the plants, or the animals that ate the animals that ate the animals that ate the plants, or whatever, how many links in the food chain there are. Okay, but inevitably, everything comes from the energy from the sun. All right, and then we're going to talk about climatograms, but that's the activity that I told you we were going to do next week, the one I had to revise a little bit so that we could do it effectively in a shorter period of time. Okay, so climate is the prevailing weather conditions at a location, and it would be advisable for you to know that the components of climate are temperature, precipitation, light, and wind. Okay, here in Alberta, okay, especially here in Okotoks, we get a fair amount of sunny days. Right? We probably get, you know, probably around 200 or 250 days of sunshine. Okay? If you go to Vancouver or Seattle or Victoria or someplace like that, they get more in the neighborhood of like 40 or 50 days of sunshine. And they get a lot more cloud, a lot more rain, okay? Because they're in a place where the factors that affect their climate are quite a bit different than the factors that affect ours. Okay? What do you suppose would be You know what? We'll get to that in a minute. Let's talk about this picture right here. Okay, this is taken on a typical summer day, okay, in Alberta. Shay, can I just have you turn off that front bank so we can see that picture a little better? What's going on in that picture? What kind of cloud is that? Hmm? Okay, it's a cumulo rain cloud. I like that. Cumulonimbus. Okay, those are the big thunderheads. You know, the ones that build up and then, you know, they deposit all kinds of disaster upon us. Okay, tornadoes and hail and all that kind of fun stuff. Okay, one of those, okay, a big thunderstorm is the result of the interaction of the various components of climate as well as the factors that affect climate. Okay, typically, what kind of a day do we get a thunderstorm on? Warm. What else? Humid. Okay. Is there much wind before a thunderstorm? No. It's typically quite a still day as well. All right? Because those are the factors we need, or the conditions that we need to build this kind of weather. Okay. Throughout the day, what happens is warm air begins to move up. But as it moves up, it's also taking a lot of evaporated moisture with it. Okay? Which means it's very heavy. It's hot air, but it's heavy. So it starts moving upwards. Okay? As it gets to a certain point, let's say they're marking on here that about 5 kilometers, okay, in altitude is about where it would be 0 degrees Celsius. I don't know necessarily about that on a warm sunny day, because I've been at 10,000 feet on a warm sunny day, or sorry, and it's quite hot at that altitude. But anyway, okay, let's say that at that altitude the temperature is 0. What's going to start happening to the moisture that's in this warm air? Is it going to stay vaporized? Or is it going to change state? Yeah, it's going to change state. It's going to go back to a liquid. Okay? Is it easier or harder to keep a liquid suspended in the air than a vapor? Way harder, because liquids are heavier. Okay? So when that stuff starts to condense, okay, the water droplets now, the liquid water droplets begin to fall back down. On a day like this, though, we have so much warm, moist, heavy air moving upwards that it can actually create a buoyancy and move that liquid water back up and push it even higher. And that's why you see throughout the day, you can watch these clouds get taller. Okay? And you've probably seen that. Okay? If you haven't, watch this summer when it happens. You can visibly watch those clouds get taller throughout the day. Right? And throughout the day, that's exactly what goes on. Okay? They're maturing, they're getting bigger and bigger. Okay? When they start to get flat on the top, that's when you need to start to worry. Okay? If they're getting flat on the top, they are about to go postal. Okay? And deliver all kinds of nasty stuff. So, this liquid water gets pushed up. It gets pushed up higher and higher and higher. So it's actually doing this. It's going through a cycle. It goes up, it kind of condenses, and it tries to come back down as a liquid. But this hot air pushes it back up again. Now, as it goes back up, some of the moisture in this air also condenses, and the drops get bigger. Okay? A light thunder shower's got small drops. A heavy downpour in a thunder shower, it's like, you know, the drops are like a pail of water. Okay? It's just a sheet of rain. Well, what if that keeps happening? These liquid water droplets now get pushed up really, really high. What's going to happen to them if they get pushed up even higher? They're going to get bigger, and they're going to turn into hail. Yeah, they're going to freeze. They'll get pushed high enough that those little water droplets will turn to ice. All right? Now, if you've got an extraordinary day where there's so much of this hot air moving upwards, those hailstones, those now solid pieces of ice, can get pushed back through this cycle several times. And every time they do, they get a little bit bigger. Yeah, the more times they go through that cycle, the bigger they will get and the harder they will get. Okay, if you ever get a chance after we've had a hailstorm, go out there and break one of them open, and you can actually see the layers inside. You can see the growth of the hailstone. Count the layers. That's how many times it went through the cycle of going up into the cloud and getting more water frozen onto it. Okay, so they grow in layers like that. Okay, and the more times they go through, the bigger they'll get. The center will get harder. Okay, and that's the stuff that can cause damage. Okay, to shingles, cars, okay, and all that kind of stuff. In fact, there's an old story from World War II that a guy who was on a bombing run bailed out of his bomber into one of these clouds, and that he actually got sucked through the cycle a couple of times and came down in a big stone. I don't think that's possible, but okay. The science of it is at least plausible because he would have a parachute, and the parachute would catch that warm rising air, and it's possible that it could have lifted him up. Okay, I don't think it could have frozen him in a giant ball of ice. Okay, but it's conceivable that he would have had quite a ride through the thunderstorm in his parachute. Okay. All right, does that sort of make sense? Okay, so without the interworkings of a warm day, so temperature, okay, sunshine, right, and a lack of wind, we wouldn't get that precipitation, right? So these things, they work together. All right, the factors that affect climate. The number one factor. So if I asked you on a test, okay, describe the factors that affect climate in Newfoundland, or describe the factors that affect climate in Zimbabwe or Brazil or whatever, okay, the one factor you should write down for every single place should be latitude. Latitude is the only factor that affects everything. Okay, and that is because latitude dictates the intensity of the sunshine you receive. If the sun is directly overhead, you receive high intensity sunshine, which means lots of energy. If you are further from the equator, then that same amount of sunshine gets spread over a larger area because the Earth is round. Okay, so if I'm looking here at the equator, okay, at 0 degrees latitude, that line there represents the width of the, or the area of the Earth that's receiving that amount of sunshine. Now, if I move that up to here, now that same amount of sunshine is covering a bigger area. My line doesn't get from the top to the bottom there, does it? Okay. And if I go even further, up to here, it's quite a bit less. And unfortunately, that's where we live. Okay. Now, that situation there, where the Earth is straight up and down and the North Pole is straight up, is only present 2 days of the year. Which 2 days? The equinoxes, right. So September 21st and March 21st. Okay, the days where the day and night are exactly the same length. Okay, for us, there's only 2 days of the year where that's true. Right? And in fact, it's that way really for every place on Earth. It's just for us, the differences are exacerbated by how far we are from the equator. Okay, I actually remember being in Hawaii in August one time, and the lady at the front desk of our hotel said, "Yeah, you know, it's so tough. The days are getting shorter." Like, what the hell are you talking about? You have no idea what it means to have a day get shorter. Your shortest day is like, what, 11 hours and 20 minutes of sunshine? You know, granted, your longest day is 12 hours and 50 minutes, so I get it, you know, but come up to Canada and live through a 4-hour day, yeah, where you get to see the sun for a little sliver of it as it crosses the horizon for 4 hours. Then you can tell me about the days getting shorter. Okay, so the further you are from the equator, the greater that difference, and then that means you get greater difference in your seasons. Right? Because at the equator, we know, they don't really get winter. Okay? They also don't really get summer. It's just pretty much the same all year round. They might have like a rainy season and a dry season, but they don't really have major changes in temperature because they don't have major changes in the amount of sunshine they receive. We do. All right? So in the wintertime, we're tilted like this. So the instead of having the axis being straight up and down like it is here, okay, the axis goes like this. And now where are we? Now we're over here, okay? Like at this spot right there. So when we actually do get into the sun, that area is going to be like even smaller, right? So we get really low intensity sunshine in the wintertime because we're even further. okay, tilt-wise away from the sun. We're not, the Earth isn't further away from the sun. Okay, people get this idea that winter and summer are caused by how far away from the sun the Earth is. The Earth is actually technically closer to the sun when we're in wintertime. Okay, the Earth's orbit is just only very slightly elliptical, right? So that makes basically no difference whatsoever. But the tilt of the Earth, that's the major thing. Now, in the summertime, which is what we're coming to right now, in fact, in what, say June 21st, so we're coming up in about, what, 16 days? 16, 17 days, we'll be in this situation. Okay, that's the North Pole, remember. So now that means that we're going to be here. That's good. Okay, sun's right overhead. Okay, we're getting 18 hours of daylight. It's high intensity all the time. We can go out and turn into little lobsters and enjoy ourselves. Okay, because we're getting high intensity sunshine in that situation. Okay, that making sense? That's why latitude can affect your climate. The further you are from the equator, the more variable your sunshine is, and the less intense it is going to be. All right, so important to remember that. All right, next one, altitude. Altitude affects your climate because the higher up you get, the colder it gets. Okay, all you have to do is look out the window and see the mountains and know that that's true. All right, our snow is gone, but there's still snow in the mountains. And it's not like they get a whole lot more of it than we do. I mean, they get a little bit more, but it's colder on the tops of the mountains than it is here. Okay, because the air gets thinner and it doesn't retain heat as well. Okay, so it takes longer for the snow to melt at high altitudes. About, guys, about 6.5 degrees for every 1,000 meters you go up. Okay, now that's on average. Okay, I used to be quite an avid climber, and I can tell you that, you know, on some days it doesn't seem to change very much. Okay, you top of the mountain, it's still really hot. Some days are like that. Okay, but in general, okay, it is going to be cooler on the tops of mountains for a longer period of the year than it is at a lower altitude. Okay, now this picture here just happened to be on a day when my my father and I were actually doing this this climb, and the difference in temperature due to altitude was really clear that day. When we left our campground that morning, which would have been way down over there somewhere, okay, at about 1,700 meters above sea level, okay, the temperature was about 16, 17 degrees, and it was kind of just a light drizzle. Okay, we got up to here. This is almost 2,000 meters higher than that, and it was pretty cold. It was near freezing. It was raining quite a bit more heavily. Okay, and you can see that up here on the top of Mount Robson, okay, which is the highest peak in the Canadian Rockies, it's a whiteout blizzard. Okay, now that would be probably another 2,000, 2,500 meters higher than this point, okay, where we were standing. All right, so quite a bit of difference. Okay, it goes from being, you know, a comfortable temperature with a light drizzle to, you know, minus whatever with blowing winds and whiteout snow conditions. Okay, and in fact, some people were blown off the mountain that day, okay, because they were stupid. Okay? You don't climb in a blizzard. Okay, unless you have a death wish, right? And they caught up with those people that day. We turned around. Okay, but yeah, so altitude makes a huge difference in temperature. Okay, so that makes a difference for, let's say, a place like Okotoks. Okay, in Okotoks we're at around 1,100 meters above sea level. Okay, you go to Canmore or Banff, okay, and they're going to be a little bit higher. Okay, they're probably closer to like 1,300. Maybe even 1,400 meters, maybe even higher above sea level. Okay, you climb kind of any of those mountains that you can see there that still have snow on the top, and they're going to be around 3,000 meters above sea level. Okay, around 10,000 feet. Okay, and it's going to be colder on the top. Okay, now that can make a difference if we're talking about a city at sea level and a city at 1,000 meters. Okay, you know, that are under similar conditions other than that. All right, next factor. Distribution of land and sea. The ocean can affect your climate, and it can affect it in huge ways. For this reason, water retains heat, and it retains it very, very well. So it can act as a regulator for your temperature. Calgary and Vancouver, and Calgary and Victoria, have roughly the same latitude. We're about the same distance from the equator. How often does it snow in Vancouver? Not very often. When it does, the whole city shuts down. Okay? How often does it snow here? Often. How often does it get to be minus 30 in Vancouver? Never. Okay? It's never minus 30 in Vancouver. Okay? How often is it minus 30 here? Often. In the winter, anyway. Okay? Because we don't have a gigantic body of water that's there retaining heat. Now, think back to last unit. The second law of thermodynamics says heat flows from hot to cold. So, if the air temperature in Vancouver begins to drop, and it drops below freezing, is the ocean going to freeze? Okay, you know how cold it has to be almost all the time for ocean water to freeze and stay frozen? Okay, I mean you look at like the Hudson Bay. It almost never freezes all the way. Okay, all the way around. I mean there might be chunks of it that freeze, right? Even out in Newfoundland, like the ocean doesn't freeze out there, and it gets fairly cold out there. Okay, but the ocean doesn't freeze. So if the ocean is still above freezing and the air tries to get below freezing, heat will move from the ocean to the air and regulate that air temperature's drop. So it can't drop that far. And in fact, really, the air can't get a whole lot colder than the ocean because the second law of thermodynamics wants to keep them balanced. So that's why it rarely gets below freezing in Vancouver, Victoria, or places that are really close to the ocean, to the Pacific Ocean anyway. The Atlantic Ocean is a little different because the Atlantic Ocean is a lot colder. All right, it's a lot closer to freezing than the Pacific Ocean is, and here's why: the nature of ocean currents. If you look at Newfoundland, Labrador, okay, those kind of places, they are here where they've got an ocean current that's coming from the Arctic. Okay, it's coming from the Arctic Ocean, the Beaufort Sea, Hudson Bay, that kind of area. Okay, so these kind of areas, sure, that ocean is going to be very cold, right? It's going to be in the wintertime only a couple of degrees above freezing, and occasionally, you know, bays and harbors and things like that in Newfoundland will freeze. Okay, the ocean water there will freeze, and then the temperature can get pretty cold. Here in the Pacific, though, you've got an ocean current that's coming from the west, and in fact, from the southwest. And what's over here? That's an A, Hawaii. Okay, it's pretty warm there, right? All the time. So you've got this current that's coming up, and this current is going to be bringing warmer water. Okay, so the ocean here is warmer than the ocean over there. Okay. So while the ocean can regulate temperature, it can do that as long as the ocean's temperature is, you know, warmer than it would be, okay, in another place. Okay, this has less ability over here in the east to regulate temperature because it's already pretty cold. Okay, and in some cases this can freeze. Okay, whereas over here you don't see this freeze. Maybe up here, okay, you might get some ice up by Alaska and places like that. That making sense? Okay, every once in a while, we get the effects of special ocean currents. El Nino and La Nina. Okay, you guys have probably heard of El Nino. People mention it often when we have a mild winter, kind of like we had this year. Okay, El Nino is actually an ocean current that happens down off the coast of Chile. Okay, so down in South America. It is such a huge upwelling of warm water that it can change the global ocean temperatures by a couple of degrees. Now, I know you're thinking a couple of degrees isn't very much. It's not. But when you think about how much water that is, that's a lot of energy. Okay? And that can result in basically everywhere in the northern hemisphere having a milder winter. Yep. Okay? Conversely, when we have those really gnarly winters, okay, that, you know, where it drops down to minus 30 and stays there forever, okay, those are El Nino's sister, La Nina, okay, and that's when we get the cold. That's when basically El Nino stops, and then suddenly all this, you know, cool water is kind of being balanced off now, and the ocean temperature drops a couple of degrees, okay, from its average, and then we get a cooler winter then. All right. Here's one that affects us. This one, other than our latitude, okay, is probably our single biggest factor that affects our climates: the presence of mountain barriers. We are very close to the leeward side of the mountains. Okay, so typically what happens for us here's the Rockies, and we've got this warm, moist air coming in off the Pacific Ocean. Okay, so it's warm, it's got lots of moisture in it, and when it hits the mountains, it has to go up. So as it goes up, it cools, and it drops a lot of that moisture as precipitation, rain and stuff like that. That's why when you go to Vancouver, you go to BC, once you get over the Continental Divide, okay, the forest and plants and everything is so much more lush. Right? Because they're getting most of this moisture to fall on their side of the mountains. By the time that moisture, or by the time that air, that same air gets to us, it's dropped most of its moisture, it's cooled right off, and now it just comes cooking down our side of the mountains. Okay? This is what we call the windward side. And this is the leeward side. We're on the leeward side. Okay? So, as this cool, dry air starts to come down the mountains, it picks up kinetic energy because gravity's pulling it down the mountains. Okay? And there's friction between that stuff and the surface of the earth, okay? And it warms as it descends. It picks up, it turns kind of that kinetic energy, it's gaining more of that mechanically as it's coming down, okay? And some of that gets turned into heat. So it warms as it descends, and then we get warm, dry air blowing off the mountains towards us. What do we call that? That is how a Chinook forms. Yeah. Okay. Now, we're familiar with Chinooks. People in Montana are generally familiar with Chinooks. But you tell people from like New York or like Newfoundland, Chinook, they don't have any idea what that is. Okay? It's just not something that they have any experience with. Chinooks are a very local phenomenon. It's a big deal to us because it happens all the time, and it's a big part of our climate. But it's a very localized phenomenon. Okay? That's how they happen. Okay? And because of the mountains, we typically are warmer, or drier for sure. Sorry, colder than this side, okay, but drier. And typically we get more sunshine because obviously that moisture isn't getting over the mountains. Okay? It gets dropped off. Now, are there places in the mountains where there's gaps and things like that where moisture can get through? Certainly. Okay? Certainly there is. And we kind of see the effects of that in the wintertime a little more. All right, so this creates what we call a rain shadow. We're in the rain shadow of the Rocky Mountains. All right, so typically you see on one side of the mountains lush forest, lots of trees, and on the other side of the mountains you see prairie, in some cases even desert. Like if you go down like Arizona, Nevada, Utah, places like that, they're in the rain shadow of the Rockies, but the Rockies are taller. Okay, and so they have a greater effect, and so they get a desert behind them. The Gobi Desert in Asia is the rain shadow of the Himalaya Mountains. Okay, so it's quite dry because they're way taller than our mountains are. Okay. Pattern of prevailing winds. Where do our winds typically come from? Not southeast, southwest. Yeah, they come from right over there. Okay, they come off the mountains. Typically, guys, here, winds blow from the west. If they're blowing from the west, from the southwest, we know what we're in for. It's going to be warmer, it's going to be drier, okay? That's typically what it's going to do. If we get a wind from the north or from the east, what's going to happen? It's going to get cold, it's probably going to rain, it's going to get nasty. Nothing good weather-wise comes from the northeast for us. Okay? Here's why. Up here in the northeast, there's typically what we call a high-pressure area. Okay? High-pressure areas mean cold and clear. Okay? Up in here is a big low-pressure area. Okay? And in fact, back in the old days when weathermen were like really important, okay, the weather guy for Alberta was Bill Matheson. He would call this the mother low, and this was the Siberian high, and these were the two things that caused all the severe weather in Alberta, and they still do. They just don't call them that anymore. Okay, so what happens is you got air that circulates a certain direction around these two things. So let's say it goes like this around the low pressure area, and it goes the other way around the high pressure area. Now what can happen is you get air masses that get thrown off of these two pressure areas. And those two pressure areas are basically always there. Okay? But they'll throw off these high pressure and low pressure air masses and send them hurtling towards each other. Now, low pressure areas typically have lots of moisture and are a little warmer. High pressure areas are typically colder and dry. But when they interact and they hit each other, they do this. and they move right down the middle of Alberta. In fact, that's basically drawing a picture of Highway 2. In the wintertime, is that where all the really bad stuff seems to happen? Yeah, okay. When we get a really bad winter storm, that's the path it follows. Okay, it follows that track because of the interaction of these two areas. Now, there's a similar situation right here in the United States. Okay, you've got a high pressure area here, you got a low pressure area right here, okay, and they interact. What's this place? That's Tornado Alley. Okay, Alberta is like the Tornado Alley of Canada. Okay, right in there you got Kansas, Oklahoma, Ohio, okay, Iowa, okay, those kind of places all in there. That's Tornado Alley. Right? Interaction of places where there's typically high pressure and low pressure has a big effect on your climate. Okay. All right. Now, climatograms. Got a little bit ahead of ourselves here. Okay, climatograms show us the weather of a location visually. Okay, and this is one of the things we're going to work on next week. All right. Here's what they show us. The line part of this graph, because it's two different graphs kind of superimposed on each other. The line part of the graph shows us the temperature. All right. So you can see one side of this has a different axis than the other. So the right-hand side is showing us temperature, and the left-hand side is showing us precipitation. All right. Now, this is Manokwari, New Guinea, basically right on the equator. What do we notice about the temperature here in New Guinea? The temperature? This is the temperature. Pretty constant, right? Hardly ever changes, because where is it? It's right on the equator. It gets the same amount of sunshine all year long. Its amount and intensity of sunlight don't change. So its temperature isn't going to change either. Okay? So it's going to be around, okay, between 24 and 28 degrees Celsius basically every day. Being a weatherman here would be a great job. Okay? You could like go away for a week and just say, yeah, it's going to be 25. See ya. Okay? And people would be happy with you. The red is the precipitation. So there's a bar graph for precipitation, and there's a line graph superimposed on that that shows us temperature. Okay, and that's how a climatogram works. And it shows it month by month. Okay, so we see down here we got the months. So in New Guinea, you can see that they get, you know, a fair amount of precipitation. In fact, they measure their precipitation in centimeters. What do we measure it in? Millimeters, yeah. I mean, if we get an especially rainy day, we might get like 2 centimeters of rain. Okay, most of the time we measure our rain in millimeters. So in a wet month, okay, this would be kind of their rainy season in here between kind of, let's say, December and April. That would be their rainy season, okay, or their monsoon season, and they're looking at getting 33 centimeters of rain, or, you know, even in a drier part of their rainy season, they're still looking at about 27 or 28 centimeters in a month. Okay, you know what happens here when we get that much rain in a month? Floods, yeah. Okay, that month, in 2013 when we got all that rain, okay, I think we got, what did they say? It was like 180 millimeters, 18 centimeters of rain. Okay, we didn't get that much. Okay, we got like half of that, and it was like terrible disaster. All right, so different places can tolerate different amounts. Now, is there a lot of flooding in New Guinea? Yes, there is. There's always flooding there. Okay, it's the same as going to Brazil, right? The Amazon is flooded half the year, every year. Okay? It's just something they deal with. All right, then they got their dry season, and of course in their dry season, okay, they're still getting 13 millimeters of rain, which would be like our wettest month here. Okay, that's their dry season, right? So what kind of vegetation? What's it going to look like in New Guinea? Yeah, it's going to be like a tropical rainforest. Okay? It's going to be a jungle, right, in that kind of an area, because that's the climate they have. Now, you look at something that's more mid-latitude. Okay, so this is kind of just above the midpoint of the United States. Okay, so we're looking at Tennessee here. Okay, so Nashville, Tennessee. What do you notice about the shape of their temperature line, though? As soon as we see that curve starting to form, we know we're moving away from the equator. All right? The curve can get more accentuated, but the curve also changes position. Here in Tennessee, the temperature curve's lowest point is like 5 degrees Celsius, and its highest point is 28 degrees Celsius. But if you look at Anchorage, Alaska, okay, its lowest point, or sorry, its highest point is about 15 degrees, and its lowest point is minus 10. Okay? Now, Anchorage, Alaska is like on the ocean too, so the ocean regulates its temperature quite a bit. If you were to draw this, for Alberta, that curve would have a greater difference between its high point and its low point, right? Our curve would be more like between those two areas. So let's say something like this. Okay, because our temperature can fluctuate huge, right? We can get summers where it's 30 and winters where it's minus 30. We can have 60 or 70 degree differences between winter and summer. All right, so ours is quite a bit different, okay, than Anchorage, Alaska, even though Anchorage is further north than we are. Okay, so it's not just latitude, it's also those other factors that we talked about that can affect your climate. Okay, and if you go to Anchorage, okay, in places like that, it's actually quite a lush looking area in the summertime. All right, the other thing you notice here, mid-latitude, what do you notice about the temperature? Or sorry, the precipitation, sorry. Yeah, there's no like wet season and dry season. The rain is pretty much the same all year long. And because of that, they get different vegetation than we do. This would be a lot like what the climatogram for, let's say, like Ottawa or Montreal or something like that would look like, where they're in a temperate deciduous forest. They got lots of maple trees and things like that that we don't necessarily have. Okay, they're much more of a deciduous area, so their rainfall is much more even throughout the year. Their temperature line is obviously going to be a little bit lower than this one. Okay, but for us, okay, our temperature line, we already said, would be quite drastic, a bit lower, and our rainfall is going to be quite a bit different as well. Okay, our highest rain is going to be June, July. Okay, those are our wettest months for sure, May, June, July. And then it would really taper off through the fall, and then might come up a little bit through the winter when we're getting some snow. Does that sort of make sense? So here's what's going to happen, what you're going to be asked to do with climatograms. The activity we're going to do is you're going to get climatograms for major Canadian cities, and you're going to try and group them together. All right, and you're going to try and find out, okay, these ones have climatograms that look similar, and then you're going to look them up in the atlas and go, oh, well, they look similar, and that's because, look, they have basically the same kind of locations, the same factors that are affecting their climate. So we're going to try and make connections between what the climatograms look like and the factors that affect climate. That's what we'll be doing in that activity. What you'll be asked to do on a unit exam and a final exam is, I'm going to give you a climatogram, and based on it, you're going to have to tell me where you think it is. Okay, now we haven't gone over the biomes yet. That's the last thing we'll cover. Okay, so basically you have to be able to look at that and go, oh, that's a tropical rainforest, or oh, that's a prairie, or that's a desert, or something like that. Okay, you'd have to be able to tell me this climatogram fits with this. All right, so that's kind of the way you need to look at them. All right. I want you guys to quickly answer those 3 questions, and then we'll go over them before the bell goes. Components of climate are, can we? Temperature, precipitation, light, and wind. And right at the beginning of class, we described what they are like in Okotoks. So let's say central Alberta is more like Edmonton, okay? But we could still say pretty much the same thing. Prevailing winds would be a little different in central Alberta. They're typically not so much out of the west as they are maybe out of the north a little bit more. But the rest of the stuff would be the same. Light varies, shortest in the winter, longest in the summer. Temperature varies with light. Okay. Precipitation is variable and comes in many forms. Right? So we would say, snow, hail, rain, okay, depending on the season. All right, what factors most affect the climate in our area? Well, the one we said we could list for any place would be latitude. Okay, we're pretty far from the equator. Okay, we're about 50 degrees north of the equator. Okay, almost 51 degrees actually north from the equator. All right, that means we're more than halfway to the North Pole. Okay, from the equator, because 45 degrees would be halfway. Right? And we are at a reasonably high altitude. Okay, we're 1,100 meters above sea level. Right? So if you were to take off in a plane here, and you could actually fly level all the way to Vancouver, you'd be 1,000 meters above the ground. Okay, when you got to Vancouver, if you if you started right at ground level here, when you got to Vancouver, you'd be 1,100 meters above the ground. Okay, it's a big difference, right, when you think about it. All right, one other factor, really big for us. Mountain barriers. Okay, in fact, I'd even say that it might even be bigger than our altitude. Okay, the mountain barriers give us Chinooks. Okay, they control really our precipitation. They cause our prevailing winds. They're huge. Okay, literally, obviously, they're mountains. They're big, but okay, they're huge in terms of how they affect our climate. All right, climate of Saudi Arabia. Temperature would be hot. Yeah, it's really hot there. Okay. What about rain? Yeah, they don't really get much of that. It's kind of a desert there. Okay. What about wind? Yeah, I don't really know either. I would assume it probably blows off the Persian Gulf, I guess. Okay. Factors that affect it, well, the Persian Gulf is right there. Okay. And they're practically at the equator. So that's a big deal. All right.